So our second kind of interesting question we're going to ask, which is something that we've kind of been putting off for a while, is where does E come from? So in Unit 6, we learned that there was this number E, kind of like pi, that we use a symbol for that has a value. And we said, in the future we learn it. We learned about ln. We had E in our formula per that just kind of showed up there. So we'll see actually where that number comes from today. So first off, before we start this, I want you to think if I was doing an exponential equation, just something like this, b to the x, what would be the simplest number you could put? Okay, so if your first reaction was to say 1 to anything is 1, so that's not even exponential. So I think it makes sense that our most simple base we could put there is a 2. So that's like the next integer. When we think about exponential growth, even on the first day, we talked about doubling being kind of like a typical example of growth. Now, when we say doubling, that means the same thing as growing by 100%. Because if I look at my basic formula, p times 1 plus r to the t, if I want to make this a 2, I would need my r to be 100% or just 1. Right, they both mean the same thing. So doubling means growing by 100%. And so we're going to think of it this way because we're going to actually need to use our compounding formula for this. So it does get a little complicated, but remember, we're just talking about the simplest type of exponential growth, which is doubling or growing by 100%. So this problem says James invests $1 in a bank account. So that also goes along with this, because if I wanted to put a start number on this, that number could be a 1, right? Simplest amount of money I can start with, simple starting number. It says this is an extremely profitable account that grows 100% interest per year. How much money will be in the account after 1 year to the nearest thousand with each compounding rate? So what we're going to do is we're going to use this formula because we have compounding rates. But remember, we're really just kind of looking at something that happens with 2 to the x, because when we grow by 100%, we're talking about 2. So when we compound once a year, so first off, the p is 1, because we're starting with $1. We're compounding once per year, so n is also 1. And for this whole problem, because we're growing by 100%, as we showed before, r is also 1. So we have a lot of 1s here, so I have 1 over 1, r over n, to the 1 times 1. Now if I was going to simplify this, this is 1. In here, 1 plus 1 is 2 to the first. So as you can see, we kind of just go back to this formula. And very simply, you don't even need to take that in your calculator. If I double or grow by 100%, at the end of the year, I'm going to have $2. So that's what happens if we don't have any of this extra compounding going on. So now what we're going to see what happens when we start to compound monthly, which means our n is 12. So all of my 1s are still there, except now I'm putting in a 12 for n. So I'm splitting up my interest into 12 parts, and I'm getting it 12 times more often. So you can go ahead and type that in your calculator. We do know that exponential, or this type of compounding is going to give us a little more money from other examples, and it actually gives me a decent amount more. I'm going to go to the nearest thousandth here. It gives me 2.613. So I gained an extra 61 cents, which doesn't sound like a lot, but I went from, $2 to about $2.50, a little more than $2.50, so that's like a 20% increase. Pretty good. So let's see, what happens if we bump this up to daily? So I set up my formula, and I put in 365. So we went from a 1 to a 12 to a 365. But what we see there, if you take that in, you get 2.715. So we only really gained about 10 more cents, whereas we had gained about 60 cents the first time we changed. So next, we're going to go up to hourly. Now hourly means that our n is 8,760 because that's how many hours are in a year, which is not necessarily common knowledge. So I'm going to take this in. Okay. And if I take that in my calculator, I end up with barely any more, less than a cent more. It rounds to 2.718. Okay? And basically, if I just keep doing this, which is kind of how exponential growth happens, right? We don't really wait for things to grow till the end of the year. If things are growing continuously, little bits at a time, doubling actually turns into this number, E, this irrational number, which is approximately 2.718. So if you type it in your calculator, you'll see all the decimals. You'll see it's if we typed in this problem and E, they're close, and the bigger we make this number, okay, the more we're going to get closer to this irrational number E, which ends up being an important number in our exponential growth formulas in calculus, and that's why they gave it a symbol, just like pi is pretty important with circles and lots of stuff with trigonometry, so they gave it a symbol pi. So that is where E comes from. That is why when we compound continuously, E is in that formula. And I will show you, this is notation that you would use in calculus. This is how we write this. So E, and I will give you a bonus point if you can write this on your test, is the limit as n goes to infinity. So this is saying we're taking this, we're going to infinity, and I'm going to write it over here. So we have the 1 times 1 plus 1 over n to the n times 1. So this is what I was doing over and over again. I'm just going to simplify it when I write it in the definition of E. So the 1 in the front, we could get rid of because that's not really doing anything. Neither is this one here, right? N times 1 is just n. So when you write this out, you usually just write this. So this is the definition. This is something called a limit. We can't actually plug in infinity here, right? Because then we would get something that doesn't make sense, right? But that's the idea. As we keep taking bigger and bigger numbers for n, E is the number that emerges. So here is the second little idea. I'm going to call this like a thought experiment because we're going to think about what would happen and then talk about how it would work. So it says, if I asked you to go out your front door and take 30 steps, I'll bet you could guess about where you'd end up without even taking that short walk. So you could look ahead of yourself and know, I'd be across the street in my neighbor's yard, or I'd be down my driveway to about there, depending on what type of structure you have for your house. And that's because it's a simple, linear, step-by-step experience you've done 1,000 times. But what if I told you to take 30 exponential steps? And we're saying an exponential step means my first step is a normal one-size step, however big your step is, say 3 feet. And then your second step is twice as big as your first one. So your second step is really the size of like 2 steps. And your third step is the size of 4 steps. So if you did this 30 times, where do you think you would end up? And I want you to think about that, get an idea of your head, like, I think I would be here. Okay? So write that down, or at least process it, and the writing it down will help you when we head to the next part, because we're going to actually figure this out. Okay. So what we're going to do is we're going to kind of think about this pattern and think about how far we'd end up. So I'm going to write this down. I'm going to write step, and then I'm going to write the size of my step, and then I'm going to write total. So we're just going to take the first step, the second step, the third step, the fourth step, the fifth step. So my first step would be step size. My second step would be a bigger step, it would be double. My third step would be 4. My fourth step would be 8. Okay, and my fifth step would be 16. So if I add up how far I've gone, after my first step I've gone 1. After my second step, 1 plus 2 is 3. After my third step, the 3 I've done plus the 4 is 7. And hopefully, let's just do one more. 7 plus 8 is 15. Do you see how your total is 1 smaller than the size of your next step? And that would continue. The next one would be a 31, right, when I added it on, and then the next step would be 32. So if we want to see how big our 30th step is, okay? That's gonna be, for my first step, hopefully we see these are powers of 2. So first off, let's just look at the fourth step. The fourth step is 8, which is 2 to the third. The fifth step is 2 to the fourth. So the 30th step is going to be 2 to the 29th, one less than the step number. And if I type that in my calculator, that is 5,000. Not 5,000. I'm going to write the number down. It's so big that I need to do this first. Okay, so amazingly, my 30th step is 536,870,012 steps. Okay? Which means that steps 1 through 29 are going to be one less than that, just like steps 1 through 4 are one less than step 5. So steps 1 through 29 are going to be 536,870,000 equal to 11 steps. So if I add those two together, that is going to give me 1,073,741,823 steps. Okay, so you can already see you were probably wrong with your prediction. But we're going to actually figure out to compare this to something physical that we can think about. Now, each of these steps, the average step is about 3 feet. So I'm going to multiply this by 3. And that's going to give me 3,221,225,469 feet. Now, no one measures that in feet, so the next thing we'd probably want to do is say, okay, how many miles is that? So I'm going to divide by the feet per mile, which is 5,280. That gives me 610,080 miles. Okay, so I don't have a whole lot to compare that to. So I looked up what is the circumference of the Earth. So the circumference of the Earth is, if you were going to go around the equator, that's 24,901 miles. Okay? So if I divide this, we can figure out how many times around the Earth is that. And if I do that division, I end up with something crazy, which is 24.5 times around the Earth. And this is just an illustration of how bad we are about thinking about exponential growth. Humans, basically, a lot of things we have to predict are in the short term for survival, if you think about being like hunter-gatherer or something, or even how short our lifespans are, and especially we're a long time ago, that we just couldn't conceptualize exponential growth, and we have this default of thinking linearly. I don't think anyone, usually if we're in class, people say like Kingston or a mile down the road or something like that. Sometimes I'll get like New Jersey or something is maybe the furthest people will say. But this problem does put us in just 30 exponential steps, 24.5 times around the Earth.